I have 4 announcements that I'd like to make before we get started. The first is my apologies. I was not there yesterday for my office hours. I had a meeting that was scheduled well before the start of the semester and before I set my office hours. However, to make it up to you, I will be available in the chat room on BSpace Monday evening at 9 p.m. And I'll hold an hour of office hours from 9 to 10. Okay? So if you log into BSpace, go to your class account, click on the chat room button on the left-hand side. I will be there answering whatever questions you might have. The other announcement, the second announcement, is about the wait list. Next week, what we're going to do is freeze the wait list for the class. This means this means that no one else can get on the wait list, and everyone who's on the wait list will be swept into the class. So if you're on the wait list now, you will be moved into the class. The third announcement is about what format to turn your homework in on Tuesday. And I'm sure you all know that Monday's a holiday, so I will not be seeing you on Monday. On Tuesday, your homework is due by 9 a.m. It must be uploaded to BSpace by 9 a.m. The upload should be in a PDF format, so you can put all of your code, your answers, your plots. You can paste them into a Word document and then print or export as a PDF file and upload that. Last announcement is that I've had a couple questions saying, is this the right thing to do for the homework assignment? And I'll say there's no single right answer to any, well, maybe to 1A there's a single right answer, but typically there's no single right answer in the problems that you'll be given on your homeworks. And it would be good for you to justify why it is you're doing what you've done. If you think that there's some doubt in your mind, you're making a choice, give a little small justification for why you're doing what you're doing. So I would like you to think about statistics and data analysis somewhat as storytelling, where you need to mix what information that you're getting or what message you're getting from the data with what context that you are aware of for the particular problem, and you tell a story. That doesn't mean it's a fairy tale, or it doesn't mean it's a long yarn. It's what you can see from the data and from your analysis of the data. And it also doesn't mean that you want to jump to conclusions. And so it's a fine art to figure out exactly what story you're going to tell, but that's the idea that I'd like to sort of follow in this class. And that's essentially what the first homework is about, is starting to give you practice in doing that. So I'm going to do something very different today. We're going to spend a good chunk of the first part of the class over there on the document camera. And the reason is I'd like to talk about R in a more abstract way. You've already been doing lots of R programming to get this first homework assignment done. And I'd like to step back a little bit and talk about variables and functions, or vectors and functions, in a general way. And the idea is that if you understand the basic concepts, then that will make your life so much easier when you go to actually trying to use R in the future for data analysis. So a lot of what I'll be talking about today is, or in this first, did I hit the wrong button? Oh, it can't tell that I've got a white piece of paper there. Okay. A lot of what I'm going to be talking about today in the first part of today, are things you know about already. But I think it'll be good for you to hear them again and see them in a more graphical or visual kind of way. So let's see how this goes. All right, so a little review about vectors. A vector is simply an ordered container. So the order piece is important. I'd like to think of a vector as this sort of long set of values. And that vector might have a name, such as x. And it might have values, and it'll have values in it. And these values come in a particular order from the top to the bottom, is the way I think about it. So even the simple x assignment statement of x equals 2 creates a vector. So x equals 2 creates a vector of length 1. So it's a vector of 1, so it's a container that has just one number in it, 2. So the way R operates is that it uses this notion of vectors. And in particular, I've mentioned this already, and I'm sure you are working with this with your homework assignments. But for example, if I say 2 times x, that takes the vector x and multiplies every element by 2. And this is the kind of thing I will get back. There are also logical operators, which I believe you've been introduced to already. And for example, I could say x greater than 1. That, again, operates element-wise, meaning element by element. It goes through the vector. And it says, is 2 greater than 1? And yes, that's the case. And so the return value is true. Is 0 greater than 1? No, it's not. So the return value is false. And then a false. And a false again. And so what we wind up with is a vector of trues and falses. Okay? There's a very special value in R, which you will run across with the babies, in particular with the gestation variable. And that's called NA, which stands for not available. That's a really important concept in statistics. If you're taking a survey and you're unable to get a response to a certain question, that's not available. If you're doing an experiment and one whole trial sort of falls apart, that's not available. You don't necessarily want to throw out that data. And you want to keep track of what was not available. And so in R, there's some default operations that happen when information is NA. And you can override those defaults, but just so that you're aware of it, if there were an NA down here in our vector, and I said 2 times NA, and what should the response be? If I have something that's not available and I want to multiply it by 2, what should the answer be? Error. It's not error, it's actually NA. So NA, we often think of NAs as errors, but they're not. We might do sometimes we might do an operation on it and get an error. In this case, though, it just gives us back an NA. And the same for this guy. Okay. Likewise, when I think about it, if I were to take the mean of x, now that's saying, okay, what's that say? It says the mean of x says add up 2 plus 0 plus 0 plus 1 plus ... and divide it by the number of entries in my vector. That's essentially what the mean function's doing. So there's a problem here. We can add 2 and 0 and 0, and we keep adding, and then all of a sudden we have to add an NA. So what happens? So what's the mean of x if there's an NA in it? Okay. Yes?
So if we add an NA to the top, I'm going to hypothesize that it doesn't actually change the top. But when we divide by the number of entries, it's going to divide by a number larger than the number of values that we actually entered.
Which isn't an error if you have more numbers on the bottom, or if the number on the bottom is larger than the number of errors. But wait a minute, let's use our logic of, you are all really ready to answer the question. When I said, what's 2 times an NA? And you all told me, no, you didn't tell me error. One person said error, or I heard one error. But what did most of you say? NA. Okay, what's 1 plus NA?
1 plus NA.
No, what's the result of 1 plus NA? NA, all right? So if I'm adding up the numbers to create a mean, I add 2 to 0, and I get 2. And I add 0 to it, and I get 2. And I add 1 to it, and I get 3. And I add NA to it, 3 plus NA, I get NA. So the mean of a list, or excuse me, the mean of a vector of values, if there are any NAs in it, part of those entries are not available. You're not going to know what the numerator is, and that will give you an NA. And lots of times we're really unhappy with that result. We want to say, you know what, I'd like to know what the mean of the rest of them are. And so then there's a special way to say, you know, throw out the NAs for this particular operation. And we're going to get to that in a second. Well, I'll get to it now. So I can say mean of x, little n, little a dot rm, that stands for NA remove, equals true. So I'm passing the mean function one extra argument that says, hey, you know what? I don't want those NAs. Get them out of here. And in which case, then I get a mean. And to get to Warren's issue of, and it's smart enough to know how many things it got rid of, and it changes the denominator. Okay. And so then I get an x bar, which I would like to get. Questions? Okay, so we're going to keep going. We're going to, today, really, we're going to go over an example, the video game example, where we had a survey of 91 students in a Stat 2 class, and you've already seen one of the questions. The response to one of the questions was, how much time did you spend playing video games in the week prior to the survey? And that was reported in hours. And so we can think of that as a vector called time. I'll call it time spent. And there will be 91 entries in this vector. And the first one might be 2, and the next one 0, 0, 1, 0, 0. You know that there were a few really large ones. There was a 14. So these are all of the responses that every student made to that question. Another question in that survey was, are you male or female? And there are 2 possible answers. You circled one or the other. So it's female or male. So again, I've got a long vector. Female, female, male, dot, dot, dot. Thinking back to the first day of class, what kind of data is this sex, gender variable? Qualitative. Nominal or ordinal? Nominal. In R, they use different words for it. They call it a factor, which is a categorical variable. Time spent, we know, is quantitative, and that's called numeric in R. So they have slightly different names for the types, and they create some more distinctions between different kinds of numbers and that sort of thing. Another question that was asked is, what grade do you expect in the class? So this was about halfway through the semester that the survey was taken. It's not what grade the professor had told the students they were going to get in the class. It was what grade the student expected to get in the class. So it might be A, B, D, etc. What kind of variable is this? What data type is this? Qualitative? Nominal? Ordinal? Ordinal. Here's one of those slippery things. I agree with you. And in fact, in R, they would also call it a factor, and it would be an ordered factor. And that's what an ordinal is. So just a slight funny thing about how there's lots of gray areas here is that you get a grade in a class, and it's given to you as a number from 0 to 4. And you have what's called a GPA, a grade point average. So in fact, you do average these numbers. So this is the kind of blurring distinction. I wrote that as A, B, C, D, which would lead you to say it's a qualitative piece of information that's ordinal. I could have done 0, 1, 2, 3, 4, and you might have said, hey, that's numeric. And you also know it could be a 3.7 for an A minus or 3.5 for a B plus or whatever, and then you'd say maybe that's actually interval or ratio data. Do you have your hand up?
Yeah, so let's say I wanted to create some code where I find the mean of all the hours that women spend. So I would create some sort of variable, we'll call it W equals sex equals female. And then that would give us a list of true statements for all women.
Yeah, you're ahead of me. I want to hold that question for a little bit. Yeah, but yes, that's a good question, and I'm not going to get there quite yet. But if I haven't by the end of class, I'll make sure to get there. So there's another concept in R, which is when we take all of these different vectors and we put them together, like this. And that's a data frame. It's also an ordered container. But this time it's an ordered container of vectors. In this case, there are 3 vectors. There's time spent. That's the first one. Sex, second one. And grades, third one. There's something else about a data frame. Each vector has to be the same length. Yes? Oh, thank you. Yeah, I should be watching this little camera here. Okay, yes. Each vector must be the same length. And what we can think of is that if we go across the first element in each vector, that sort of creates what we call a case or an observation. That observation is the answers from the very first person for the survey. So we'd say the first person spent 2 hours playing video games, is female, and expects an A in the class. And as we go down, looking at the 10th element in each of those vectors, that corresponds to the 10th case, the 10th respondent to the survey. Okay? Any questions? One more thing, which you already know, is if you want to try and do some kind of operation, call a function on one of those vectors and they're stuck inside of a data frame, we could, in this particular case, I'm calling this data frame video. And if I want to take the average time spent playing a video game, I would take the mean function and say video dollar time spent. So that dollar sign is a way for us to access the particular vector in the data frame. So the key concept are these vectors are ordered containers. Everything in that vector has to be the same type of information. Then if we collect a bunch of vectors, that collection, again, is ordered. And it's a collection of vectors, which we call a data frame. Those vectors must be the same length, but they don't have to be the same type. So I now have a data frame with 3 vectors. Each one of them is slightly different. As far as R is concerned, there's a numeric vector, a factor, and a factor that's ordered. Okay? So we haven't seen any code. Well, we've seen a little bit of code, very little code. But basically, we're trying to get the concepts across through these pictures. All right. Now I want to turn to functions. Oops. So in particular, we want to think of a function as something that does something on some data or on some values. And so let's look at the mean function. The mean needs to take in some data, x. And what it does is it adds up all the values, x1 to xn. So this is just an abstraction. It's not code. It's an abstraction of what the mean function's doing, and it divides by n, the total number of elements in the list. And then it gives an output. So this is the output. This is the input. And the output is what we would think of as x bar. It's got a type. In fact, what it is, it's a vector with one element. Okay? In fact, the mean function has more than one input argument. It's got 3. It's got one called trim, and another, which I just showed you, na.rm. Those are also inputs to the mean function. These two have default values. So if you don't supply them, R knows what to do. The default of trim is 0, and the default of na.rm is false. What do these do? I'm going to make my function a little bit bigger and say what na.rm does, you know already. It eliminates, well, it says whether or not to eliminate the NAs. So I'll write that as a question mark. It's asking, should I eliminate the NAs? And its default is false. Don't eliminate them. Keep them in the computation. And you can change that to true if you would like to eliminate them. Trim says, do you want me to trim the largest and smallest values? It can have a range from 0 to 0.5. 0.1 says cut off the lowest 10% and the upper 10%. The default is 0, which says don't do any trimming. Don't throw any data away. Just use everything that you've got. You can find out what the arguments are to a function by calling a function called arg. Arg paren mean gives you the arguments. And question mark mean not only gives you the arguments, but tells you what kind of information it's expecting and what it's going to do with it. So if you already know how to work a function, you just have forgotten what the name of the argument is, you do arg of mean. But if you don't know how to use the function, you do question mark mean and read through the documentation. All right, so let's, what I'd like to do now is talk to you a little bit about how on earth we call this function with 3 arguments. So essentially, if we look at how the mean function, what we call its function definition, it's listed as mean x comma trim equals 0 comma na dot rm equals false. Notice it's all caps, the false. So that's the typical function definition. It says I have 3 arguments, and they have names, x, trim, and na.rm. Those are the names of my arguments that go to the function, the inputs into my function. The first one, x, doesn't have a default value. It just is there as x. That means it's required. You can't call the mean function without giving it the data that you want to take the mean on. So this is required. And these two are not required. They have default values, which they will use if you don't supply them. Okay? So the very most precise way to call the mean function and pass it the arguments would be by argument name. So there's 2 ways to specify values for an argument. The first one's by name. And so we could say mean, paren, x equals time spent, trim equals 0, na.rm equals false. So you've specified every single argument, given its name and what you want in there for the value, what the input's going to be. It says, hey, for x, that's the stuff I want to take the average of. Here it is, time spent. Hey, for trim, I don't want to trim at all. Here's my value, 0. Hey, for na.rm, I'm not going to remove anything. Make that false. Okay. Now, you don't need to specify the name. You don't need to specify the arguments when there's a default value. So I could just as well have said mean x equal time spent. And then all the defaults are taken. So here I'm also using the name of the arguments, and I'm relying on the defaults. Question?
Do you have to extract the time spent vector, or does it just...
Oh, I'm ignoring that detail of do I have to extract the time spent if it's in a data frame? Yes. So if it were in a data frame, I'd say video dollar time spent. That's exactly right. Otherwise, it can't find it. It can't find the variable. And when you get an error like that that says object not found, then it's like, oh, either I mistyped it or it's inside a data frame or something like that. You're welcome. The other is by position. You can specify arguments by position. And so I could say mean time spent, comma, 0, comma, false. So here it actually matches up the order. The first argument must be to x. The second argument must be to trim. The third argument must be to na.rm. So just to back up a little bit, I could have, in the first case, I could have actually said mean, paren, trim equals 0, x equals time spent, like that. And they're not in the order of my function definition, but it doesn't matter because I've given their names. So that's matching by name. Says you can put them in any order you want because you're telling me what name the argument is. If you don't do that, then you're matching by position. And just to complicate things a little bit more, you can mix. You can match by name and position. So last sort of complication is, okay, a mix of name and position. And so here's an example. Mean of trim equals 0, comma, time spent. So what R is going to do is it says, well, I've got 3 arguments. I've got x, I've got trim, and I've got na.rm. My default for trim is 0, and my default for na.rm is false. So now she's given me 2 arguments. The first one, it first goes by name. It says, OK, she's given me trim. So I'm going to go and I'm going to put that in there of 0. And then it looks around and says, oh, she hasn't given me any others by name. So first you do the by name. Then the leftover ones you fill in by position. So what's left over is time spent. Well, that must go in the first open spot, which is the x. And it says, well, what about na.rm? Well, fortunately, there's the default value, and that gets put in. So, everybody with me? Here's one for you. Mean. Trim equals 0. True. Time spent. And I've got my 3 arguments that the function's expecting. X, trim, which has a default of 0, and na.rm, which has a default of false. First thing, what do I do? Trim, because I've named it. And so I take the value of trim and I stick it in there, and that's 0. Do I have any other named arguments in my function call? No. So I start matching by position. What's the first argument that I'm supplying the function? True. Where does it go? It goes into x, because it's the first, and I match in order by position. And then time spent goes over here. And what happens? Error. It'll say, well, hopefully, if there's a lot of good error checking, it will say, hey, you've got an error here. I was expecting a logical for na.rm, and you didn't give it to me. So that's how function mapping happens. Any questions? No? Just for those of you who are really into this kind of thing, 2 more things. Is that even the star for multiplication, the plus for addition, the greater than symbol for logical are operations, are functions. If you're really weird, you might want to call them like they're functions. So when I said 2 times time spent, or 2 times x, remember I said 2 times x. That's not the syntax or the format that we've been calling all the other functions in. We've been giving the name, paren, the arguments for the function. If you really want to, you can do that with multiplication as well. But you have to do something special. You put a single quote times, single quote, paren, x, paren. You can try it in R the next time you're doing it, and you'll see that, in fact, that works. You can actually call multiplication in the same kind of function format if you'd really like to. I don't suggest doing it because it gets kind of confusing after a while, but it's there. And last thing you've seen already are compound functions, or compound function calls, which is calling a function within a function. So in other words, we could even mean of 60 times x is a compound because the multiplication is a function, but also mean of sort of x is also a compound function call. First you sort x, and then you take the mean of it. And you don't get anything different than if you just took the mean of x, because it doesn't matter what order the numbers are in. All right. Now that we have gone over about vectors and data frames and functions, I'd like to now go back to the Stat2 survey, and we'll do some analysis. We'll look at lots of different kinds of plots of these data And I'm not going to focus on the R code, but the R code's going to be on every single slide. I'll post these slides, and you can therefore look to see what code produced the plot. Okay, so we've already talked about the survey being of 91 students enrolled in Stat 2. We collected many variables, but here are just 3 of them: the time spent, the sex, and the grade. And there's the vector for time spent. It's 91 long, and you can sort of look across and see that there's a 3 in there, there's a 14, there's a 30, there's another 14, but there's a whole bunch of zeros. So again, vectors are ordered, and in this case, there are 91 elements in it. We've already covered this on the document camera, so I'm just going to breeze through it. What is a vector? Just so you know, if you want to know what the different possible values are for a factor, you can call levels, the function levels, pass it the factor vector. Levels of grade tells you it's FDCBA. Table's a wonderful function. When you have a factor, there's not a lot you can do with factors aside from tally up how many fall into each category. That's what table does for you. It tallies up how many F's, so B, F, D, C, A, B's, etc. Question for you. This is what the students expect to get in this class. What do you think of that table? Yeah?
I think the C's are realists.
You're saying there are a lot of optimistic people in this class. Right. Okay. This was Stat 2, and if you take Stat 2, you probably know that it typically has a very strict curve or quota where nearly 40% of the class gets C's. And you don't see even close to 40% of the people expecting C's. We have another, later on we'll show you yet another interesting observation. So what are we doing here? I'm using context. I'm using context to interpret these results. The context is I know that there's a strict grade distribution for Stat 2. And I'm thinking, how does what people think compare to that grade distribution? That's the kind of thought process I want you to do throughout this class and to get started on the first homework. You had a question.
Yeah, I noticed that when I was working with the program, table and summary.
Yes.
What is the difference?
Table and summary. What's the difference? Table is more sophisticated. It allows you to actually take a table of 2 variables. So it would could do a table of sex by grade. And so you can pass it sex, comma, grade, and you get a little table to see how the females, what grades they expected and what grades the males expected. Summary doesn't do that. Summary, depending on whether you have a factor or a numeric. If it's numeric, you get things like means and medians. And when you've got a factor, you get something like table when it's just a single variable. Table does more things than that as well if you look at some of the arguments. But that's the idea. You can, there's an exclude argument to table, which says, you know what, I don't want to see these particular values. So if there are, for example, unknowns as one of the factors, you could exclude an unknown from a table. That's okay. Vector operations we talked about. So I'm going to move along. Missing values, the NAs we talked about, and functions and inputs to functions. And it's all here what we just talked about. So I'm now going to go on to start looking at our plots. All right. So here I've called plot of density of time spent. So density is producing sort of what those smooth versions of all the observations are. And plot says, oh, I know how to plot the results of a density, and it's producing this result. The main equals, main's an argument to plot. There's a default to main, so you don't need to supply it. But if you want to put a pretty title on your plot, you say main equals, and then in quotes you give whatever title you want to have there. And so again, we've seen this interesting distribution, which we saw on Wednesday, of a very big spike at 0 and then a few other little peaks at sort of typical times that someone who plays might spend in a very long right tail. So here are some other arguments to the plot function. So there's main. There's also xlab if you'd like to put a different label on the x-axis. There's xlim if you'd want to say, you know, I'd like my plot to start at 0 and go up to 50 or something like that. Likewise, there's ylab for the y label, and there's ylim for I'd like my plot to go from here to here in terms of what my axis, from 0 to 2 or something to that effect. The defaults that R produces are very good. So oftentimes you don't need to touch any of this. And col is for color if you'd like to color the curve in the density plot or the points in a scatter plot, etc. We're going to go over a lot of these next week. I'm not expecting your plots for your first homework to look beautiful. I'm expecting you to focus on trying to interpret the results. For the next week and a half, we're going to do lots of things about how to make graphs much more meaningful and convey information in the best possible way. So don't focus too much on these for right now. What about qualitative data? We haven't talked about that yet. How do I represent qualitative data? Again, what we can do is sort of tally it up and report how many or what percentage belong in each group. There's essentially what I see as two basic ways to tally it up. One's with a bar plot, the other's with a pie chart. So a bar plot, again, there are bars. The width of these bars have no meaning. The height of the bar tells you the number or percentage, depending on how you've created it. This is the number in each of these categories. So F and D are empty. There's 0 people expected, a D or F for the class. There's the C's, the B's, and the A's. The pie chart is very similar, where the piece of the pie, the area of that piece of the pie, tells you what proportion. And notice that what input these functions, bar plot and pie, expect are the counts for each of the categories. And so the table function produces them. So you can say pi of table, it's a compound function now, pi of table of grade. And there's the exclude argument, which says, hey, you know what? I don't want to see the D's and the F's because I know those are zeros. Yes? Yes. Well, the bar plot doesn't have the exclude argument in it. The pie chart does have the exclude argument in it. And what happens is the D and the F will fall on top of each other at the right where between the A and the C piece, because there's no area. So it's just going to plot lines right on top of each other. You could, instead of doing these compound functions, you could do a sort of step-by-step approach where first you could create the vector for what you want to exclude. Then you could create the table and save that to tab grades. And then in the end, you say pi of tab grades. So you could do a 3-step process, or you could do this sort of compound, create one formula at a time. So it's up to you as to whether or not you think it's easier to see this 3-step process or to shove it all into one call. If you're starting, just beginning, this approach might be much easier for you to say, okay, I'm going to exclude D's and F's. So I'm going to create a vector of the levels that I want to exclude. That's what exclude vector equals C. Remember, that's catenate D and F. Notice the quotes. Then I'm going to create a table of counts for the remaining levels for my factor. So table of grade, exclude equals exclude vector. So I'm passing it the vector. Then finally, I'm going to take a pie chart. I'm going to make a pie chart of those counts. So it's pi of tab grades. So that's exactly the same as this bottom line. Pi of table of grade exclude equals CDF. So whichever one you're most comfortable with. Oftentimes, and this is, we want to make comparisons. Not only do we want to look at the distribution of time spent playing a video game, we want to compare, as someone mentioned already, females and males. We might want to say, well, what's the time spent playing a video game? How does that compare between males and females? And in this case, what we're saying is we've got a quantitative variable, time, and we've got a qualitative variable, sex. So we want to look at time for the different levels of our qualitative variables. We want to look at the distribution of time for the males and the distribution of the time for the females. We can specify this with a formula in R, which is time spent tilde x. That says I want to see how time spent depends on sex, gender. Okay? So here's some of you are asking about unique plots. Here's one. This is what's called a violin plot. What it is it's like a density plot on its side and then mirrored over to make it look pretty, and that's why they call it violin plot. That's in a special package called Using R. So if you'd like to use this for your homework, you first have to install that package. Once you've installed it, then you can call it library paren using R. I want a violin plot of time spent tilde sex, and I'd like to color it bisque. So you can see right away that it's the males who are spending more time playing computers than the females. Not a big surprise, but there it is. Or you could make comparative box plots. We will get to those on next week, so don't worry about it if you don't know what a box plot is. Just don't make those. We'll get to those next week. Now, what about wanting to compare a qualitative variable with another qualitative variable? Like, how does a distribution of grades change by sex, depend on sex? So do you think the males and the females roughly expect the same proportion of females expect an A as a proportion of males expect an A? Before I show you the plot, what do you think? Should that be the same? Yeah, I think you're saying yes. Here's a mosaic plot. So that's a different kind of plot as well, another one of these unique plots. This says, I want to see how sex depends on grade. A mosaic plot, we work with two qualitative variables. What we see with this plot is that, first of all, all the gray shaded boxes on the left represent, out of the total area, represent the proportion of females in the class. So we see there are fewer females than males. That's not what's interesting to us. What's interesting to us is that if males and females expected A's with the same proportion, then the box on the left would be cut up in the same sort of fractions as the box on the right. And it's not even close. There aren't any males who expect a C in the class. All the people who expected a C in the class were females. Not only that, the males are twice as likely to expect an A in the class as the females. Do you think the grading actually happens that way in the class? No, it doesn't. So that's kind of interesting, right? Yes?
So you just tell which box refers to which grade by like what order rank?
You can, it might be hard to see, but there's a little letter on the side here that says A, B, C. And at the top it says female, male. And so this whole left column of boxes are for the females and the right ones for the males. Yes?
If, for example, the males, none of them expected B's, and that box was on.
Then there'd be a little line. Just like at the very top there are those little line segments. That's because there's no area to that box because no one's expecting a D or an F. There's a placeholder so you know that there's no one there. That's exactly right. So it's really interesting when we start looking at relationships between variables. This is how you look at relationships between two qualitative variables. The violin plot is a way to look at the relationship between a quantitative and a qualitative. And if you want to start looking at relationships between two quantitative variables, you use the plot function as well. And you plot, this in this case is plotting time on the x-axis and plotting the amount of hours that you work for a job for pay on the y-axis. So again, you can use that same tilde formula, plot of work tilde time, and you get a plot that looks like this. I didn't get to your question. I can answer it.
You actually answered it.
I thought I might. I thought you might think this was satisfactory, but you can still do what you're talking about as well through a different mechanism. Have a very good weekend.